In this video, I want to talk about the current divider circuits. So like we saw for the voltage divider circuits, in which we sometimes needed to create some additional voltage levels for our circuits, sometimes it's also necessary to divide the current from a single current source as well. So one way of doing this is by using a current divider circuit. So here you see a very basic example of a current divider circuit. So we have an independent current source with the current Is that is connected in parallel with two resistors. We have R1 and we have R2. So since they are connected in parallel, we know that they all have exactly the same voltage. So here we have voltage V shown with this polarity, positive on the top and negative on the bottom. So the voltage across all these three components, the two resistors and the current source, is exactly the same. So what we can do here is now we can write the KCL for this specific circuit. So based on the KVL, we have V to be equal to R1 multiplied by I1, which again equals R2 multiplied by I2. So the voltage across R1 is R1 multiplied by I1. The voltage across R2 is R2 multiplied by I2. And this is equivalent to the voltage that we have across this voltage source too. And since we have this current Is going in this direction, and we have R1 and R2 to be in parallel, we have this equivalent resistance too, as a result of R1 being in parallel to R2. So this equals Is multiplied by Req. Do you remember what was the equivalent resistance for two resistors that are in parallel? It was R1, R2 divided by R1 plus R2. So that is Is. So now that we have this, we can find out the current for each one of these resistors. So what is I1? So I1 is V divided by R1. So from this equation. What about I2? I2 the same. It is V divided by R2. So we know the value for V from this equation. Since we know Is and we also know R1 and R2, we can easily find the equation for I1 and I2. So we have 1 over R1 multiplied by R1, R2 divided by R1 plus R2 Is. So this is 1 over R1 that we have here, and this is V. So if I do the calculation, this becomes R2 over R1 plus R2 multiplied by Is. Let's just do the same for I2 as well. So for I2, we have 1 over R2, the division that we have here, multiplied by V, which is R1 multiplied by R2 divided by R1 plus R2 Is. So in the top line, you saw that R1 here and here got cancelled. Here, R2s will be cancelled. So we have R1 over R1 plus R2 multiplied by Is. So this is I1 this is I2. So let me just write this quickly. So R2 over R1 plus R2 multiplied by IS, and I2 is R1 plus R2 IS. So as you can see here, when the value for R2 increases, the value for I1 also increases, and vice versa. For I2, when the value for R1 increases, the value for I2 increases. So in effect, the current that goes through I1 is dependent on the value of R2, and the current that goes through I2 is dependent on the value of R1. So if you think about it, that makes sense. When you have these two circuits, right, and you know from the KCL, if you write it here, you know that IS equals I1 plus I2. So that's something that you can easily write using KCL and at the top node. So the sum of I1 and I2 always equals IS. And since this is an independent current source, that means that it always maintains the value for IS. So what happens is that when you have R2 to be smaller than R1, based on these two equations, when R2 is smaller, that means in this path there is less resistance to the current, which makes it having more current than the other one. On the other hand, when R1 is smaller than R2, this path has less resistance to current. So that makes it having more currents. So think of these as two lines of water. So two water paths. Having a lower resistance means that the path is wider. So less resistance, more current. So these are something that can be verified using these equations as well. So we did the calculation, and what conceptually is acceptable, we saw it here too. So I2 is in direct relationship with value for R1. When R1 is higher, that means I2 becomes higher. When R1 is lower, that means I2 becomes lower. So this is something that you should keep in mind. So for the voltage divider, first of all, we had two resistors to be connected in series. Whichever had the highest amount of resistance got the bigger portion of the voltage. For current divider, we have these two resistors to be connected in parallel. Whichever has the lowest amount of resistance gets the highest portion of the current, and vice versa. So these are the same basically calculations. So again, note that if R1 is greater than R2, then I1 is smaller than I2. Again, since higher resistance or higher amount of resistor means that higher resistance for the current. So the resistor with highest amount of resistance gets the smaller portion of the current. But of course, the sum of the two currents always add up to IS, right? Because these nodes don't consume any currents or don't produce any currents as well. So now that we have this, the question becomes, how can we generalize it to more than two resistors? So the answer to that is very straightforward. So here we have this current, this circuit that provides this fixed current to these resistors that are all connected in parallel. So since all of them are connected in parallel, the voltage across them is the same. So the voltage across Rn is the same as Rn minus 1, same as Rj, same as R2, same as R1, and same as here. But what we can do is that we can write the KCL at this node. So let's just quickly write the KCL at this node and see what we get for the generalization of the current division circuit. So we have negative I, since it's entering this, equals I1, or negative I plus I1 plus I2 plus all the way to Ij plus In minus 1 plus all the way to In equals 0, or I equals I1 plus I2 plus all the way to Ij plus all the way to In minus 1 plus In equals 0. So what are these individual currents? So since the voltage across them is all the same, I becomes V multiplied by 1 over R1 plus 1 over R2 plus all the way to 1 over Rj plus all the way to 1 over Rn minus 1 plus all the way to Rn. So this, if you remember, is equivalent to 1 over Req for a bunch of resistors that are all connected in parallel. So I can just simply write it as V over Req. So now, based on this equation, we can easily write I equals V over Req, or V equals I multiplied by Req. So now the question is, what is Ij? We are looking for Ij. Since we have the equation for V now, Ij equals V over Rj, or I Req over Rj, or Req over Rj multiplied by I. So this is how we can generalize the simple two resistor current divider circuit into having more than two parallelly connected resistors. So as you can see here, when Rj becomes large, the value for Ij becomes smaller. So they are inversely proportional. Lower value for the resistor means higher current. Higher value for the resistor means lower current. So this is the conclusion that we have and the generalization that we have for the current divider circuit. So in this video, you got introduced to basic current divider circuit, and then later on we generalized it to having more than two resistors all being connected in parallel, and we found the equation for the current that goes through each one of those resistors individually.